Hello everyone. Welcome to my talks. It's my pleasure to introduce today's speaker, Aran Nayabi. So, Aran is a tenure-track professor at Machine Learning Department at Carnegie Mellon University, a core faculty member of the Neuroscience Institute and courtesy member of the Robotics Institute. His work bridges neuroscience and AI to understand animal intelligence and build better autonomous agents. Today, he will share with us how he can use self-supervised model trained for embodied biomechanical realistic control tasks that can actually align more closely with the neural recording data from rodents and primates. Please join me welcoming Aaron. Yeah.
Thanks so much for the invitation and introduction, Hokin. So today I'm going to be talking about two case studies in rodents and primates that fall under a broader theme of using embodied AI as a framework to help understand structure and function in neural circuits. In particular, both of these works will demonstrate a positive correspondence, an unexpected one actually, between self-supervised learning of visual representations that are relevant to high-dimensional embodied control and increased gains in neural predictivity in multiple species. And at the end, I'll have kind of like an informal reflection on the talk, in particular talking about heuristics for interrogating natural intelligence that come out of this endeavor of connecting embodied control with neural predictivity that may be of interest to this audience in particular. So one motivation for this comes from this kind of like maybe by now kind of standard like brain score plot of looking at ImageNet performance on the x-axis versus single site neural predictivity in macaque v4 and IT. And in particular, each dot is a ConvNet model that's trained on ImageNet, and we're comparing how well its internals after task optimization to do categorization match visual areas in primates, both the middle areas like V4 and the higher level areas like IT towards the top. And the main thing I want to point out is that among very different CNN architectures, despite them being largely very different, we see actually very similar neural predictivities to macaque V4 and IT. Basically, there's an initial trend line where the better you get an ImageNet, the better of a neural predictor you are. But past, say, about 70% top one, especially on the right, you see the models start to like tap out, basically. This is, you might say, well, like, oh, is this something that's like particular about this particular data? Well, even humans, so this is human occipitotemporal cortex, so the analog to visual to those visual areas that I was showing you in the previous plot. And what they see is this is in work led by Colin Conwell and others in Talia Konkel's group at Harvard, that there's quite similar predictivity of these areas between not just different CNNs, but between CNNs and transformers. So what this suggests to me is that we're kind of tapping out in terms of building brain models, especially in sensory areas, and that new ideas are needed. The different inductive biases of a transformer aren't buying us increased gains in predictivity really over to the CNN. Now, we could ask, does this source of new ideas comes from having better models or from improving and more fine-graining the type of methodology that we use when comparing models to the brain? And I'm mostly going to argue, I'm going to show you that the argument really rests on having new models. But to do so, I'm going to first dive into the methodology. And basically the question I'm going to ask is, are we actually just reaching the ceiling of these current data without knowing it? So how do we go about determining whether our methodology is even correct of mapping models to brains? Well, one thing to point out is we don't have an a priori notion of what constitutes a good brain model in an absolute sense. We don't know ahead of time what's going to be good or not. Because if we did, we would just put in the model and be done already. We wouldn't do this kind of careful and like continuous empirical model to brain comparison if we already knew what to put in to be brain-like. So we had some recent work with wonderful collaborators, Janelle Feather, Meenakshi Khosla, and Ratan Murthy, showing kind of just like defining a notion of a NeuroAI Turing test that comes from a lot of this work anyway, where the basic idea is that we know that whatever those properties are that make something brain-like, they're in the brains of the animals and the subjects that we study. They may not always be in the model, but they'll be in the brains because that's the target of comparison. So even if we can't describe them in absolute terms, we know that they are in the brain. So what we do is we take a relative perspective. We say that a model should be as good as a model of the brain as brains are to one another. And the inspiration from this, the reason why we call it a Turing test is that, the standard kind of classic Turing test of intelligence was that, if a model acts like a human as well as humans can distinguish humans from one another in behavior just from the outputs, then that's a model of intelligence. But of course, if we just look at the outputs of something, that's not always going to be discerning about what's actually going on underneath, right? So here is a silhouette of a rabbit, which could be created by an actual rabbit or by our hands, like hand puppets. Whereas the NeuroAI kind of update to the Turing test is that we should also not only look at the outputs, behavior is important, you got to do intelligent things, but you should also be matching the brain in the internals as well at the actual level of the firing rates too. And so not only do we compare we want the models to match the brain in terms of behavior as brains are to each other, but we also want to match brains as they are internally to one another. There's inherent variability basically between brains due to evolution, even when you fix the same exact stimulus. And so on any metric, the brain won't be perfect, but it'll be some number, and that's the number we want to reach. So let me just illustrate some possible scenarios. This is just a cartoon just to show. One is that no models reach the brain-to-brain similarity score, which is the NeuroAI Turing test that we're looking for. And the models are the bar plots here. So what we do is, in that case, is if we haven't reached the brain-to-brain similarity ceiling, then we continue to refine the models to improve on the benchmark. On the other hand, if the models do reach the brain-to-brain similarity, then that means that we've basically saturated this benchmark, and then we should move on to other benchmarks. So going back to our example in primate object recognition, each bar here is in this case was a ResNet 18. This is adapted from our Convar work in 2022. So at matching to the IT neural data that I was showing you earlier, and we're looking at different time points in the IT data to show that across different time points, so 130 milliseconds or 200 milliseconds, and across different mapping types, so different types of linear regression, in this case, the number of components in PLS being varied on the x-axis, what we see is that we get quite close to the noise ceiling, to the NeuroAI Turing test in each of these. In fact, we're about 90%. Whereas the standard kind of statistical noise ceiling would have you thinking that you're much further away than you actually are. So perhaps what we've actually done is shown here is that we've actually probably pretty much tapped it out for at least this kind of classic IT data set that the NeuroAI community at least has kind of really looked at in terms of benchmarking for object recognition. But what I'm going to show you is that we're quite far from this kind of even this NeuroAI Turing test, not just for like basic object recognition, but for embodied, more broadly embodied intelligence. So to do so, this is going to motivate the case of trying to build better models. And one, way of getting out of this kind of local minimum of ideas is to kind of think cognitively, right? Think about the kinds of visual behaviors you and I engage in. So just to illustrate, again, a lot of these models in the past were trained on ImageNet. These are real ImageNet images where the task was basically to take the object that's in the center and be able to correctly categorize it. Now, our visual systems support a lot more than just looking at static images in perfect lighting, right? For example, we can rapidly recognize objects and scenes in a variety of scenarios, despite a wide range of viewing conditions. But we can also go beyond that and see the relations between objects, namely in this case that cars are supported by the road, people walk along the street, buildings and trees line the sidewalk, all of which constitute a rich understanding of the scene. Furthermore, animals, not just humans, can make complex multi-step plans to attain desired targets. So here, what you're seeing is a crow using a stick to grab food that it couldn't otherwise reach with its beak alone. Animals can also navigate and effortlessly explore novel environments. So depicted here is a top-down view of a rat in an open environment where the red dots indicate the place cells that are firing in its brain, in particular its hippocampus, as it navigates and enters a particular location in its cage. So it creates a kind of cognitive map of its environment. And finally, animals can control their bodies with ease to masterfully interact with and manipulate their environment, greatly rivaling any robot that we have today. So the crucial thing I want to emphasize here is that all of these behaviors are done in a body. And so as someone who's interested in brains and in AI, I'm interested in how the computations in our brains actively reformat this dense sensory information to be able to enable these behaviors. And typically, the way neuroscientists approach this question is to study it in a bottom-up way, but this has only yielded understanding in very limited scenarios because we can't write down simple handwritten rules for these behaviors across the messy and challenging environments humans and animals confront every day. So how might we go about understanding the means by which our brains actually implement these computations to bridge the gap from neurons to behavior and to scale to these challenging environments? And so what I'm going to do is I'm going to show you that performing visual tasks out of the box, given space and energy constraints, in general in environments where there isn't a single well-defined category label for that scene, which foreshadows using self-supervised learning, correlates well in terms of providing a tight connection between that and general scene understanding to be able to do flexible embodiment, resulting in an overall good neurally predictive model. So in the rest of this, I'm gonna first focus on mouse visual cortex, and then what I'm going to do is then make a change of species and behavior to study a more higher cognitive domain of mental simulation of future scenes in primates. And then I'm going to end on some heuristics for interrogating natural intelligence that maybe some of these studies kind of direct us to. So what I want to emphasize is that we didn't study mouse visual cortex because mouse visual processing is any more interesting than in primates, but really to interface in a compact way with higher cognitive functions in an animal model that's relatively common in systems neuroscience. And so, and what happens is like we found out that like a quite good model there actually ends up having a connection to biomechanically realistic control. So this was work that I did with my collaborator Nathan Kong and others that appeared in PLOS Bio a couple of years ago. And the basic idea was that if I look at this plot of matching IT, matching the brain on the y-axis, each dot is a model, and doing better on ImageNet, right? I see this kind of tight connection between a neuroscience goal of explaining variance in brain responses and this AI goal of doing better at accuracy. But the natural question is, does this hold in mouse? So here we have a different species altogether, and furthermore, its visual system is far less hierarchical, right? So it literally looks like a paw with like V1 in the center here, occupying most of the mass, and then the higher order areas kind of read off of it in parallel. It's not at all hierarchical. And what we see if I make the same plot for mouse, we see like not a R of correlation of 0.92 of doing the task better versus predicting the neurons, but actually a slight anti-correlation of like negative 0.17. So in fact, as you get to be a better object categorizer, you're actually a worse mouse model. So a natural question is, does like optimizing for a task actually apply to the natural intelligence in other species like rodents? And I'll tell you, yes, it does, but it just comes down to identifying a different set of constraints. So long story short, the best models that actually match the mouse, and so on the y-axis is the raw neural predictivity, so it says 0.41, but if you do the animal-to-animal consistency there, the NeuroAI Turing test for this mouse visual cortex, you get this is like about 90% of the NeuroAI Turing test in mouse visual cortex as well. And the models that people started out before, which is the model on the bottom right that's black here, was about 56% of the NeuroAI Turing test originally. And so what we see is that models that are trained in a contrastive self-supervised objective, which is something you could reasonably get from head motion, where you say that different views of the same image or the same object and different objects are contrasted as negative samples, that are shallow but self-supervised in this contrastive way, end up being the best models overall of mouse visual cortex. And so one thing we wanted to understand was why was this happening? What might be the ecological reason why the mouse visual system prefers self-supervision? And our hypothesis was that it's trying to learn as general of a task representation as possible while subject to the resource constraints it's faced with of a much shallower cortex than in primates. So rather than spend all its resources being really good at categorization, it's more kind of spreading them across a bunch of tasks through self-supervised learning. So the way we assessed this was we pre-trained our in silico mouse visual cortex, and then we evaluated both in a new setting, but also a new task of, in this case, reward-based navigation. The way we did this evaluation is that we took our in silico vision network that was pre-trained, fixed its weights, so froze the weights, and then we dropped it into a biomechanically realistic rodent body that had been developed just a couple of years prior by Ben Solvecki's group at Harvard. And then what we did was we only trained a decision-making module on top, a policy to be able to basically navigate this maze and get a reward every time it got this blue orb. And so what I'm going to show you is like after training the policy, the first-person view at the resolution of the actual mouse in this biomechanically realistic body. So you see it basically going and then getting these blue orbs and getting reward, and then it resets. So this is after learning with this visual cortex that we've created. And so I want to emphasize this isn't just out of distribution generalization, right? It's like a different task altogether, involving not just visual recognition, but controlling a high degree of freedom body and keeping track of history over long time scales with high dimensional inputs. And so what we see is that if we took the same version of this visual cortex, pre-trained it on categorization, so fixed the architecture, fixed everything, but just changed the loss function to be purely categorization in the black bar versus contrastive self-supervised, the mean episode return of the contrastive model, which better predicts mouse visual cortex, is higher. We can also go the other direction where we train a bunch of tasks with the same kind of difference in loss function between the maze environment pre-trained there rather than on ImageNet, and then evaluate in a completely different like visual scene understanding environment. So that allows us to test things like pose estimation, position estimation, size estimation, object categorization, and texture categorization, where the supervised signal in this case is actually the RL signal. So it's supervised there. And again, you see that overall the contrastive, the self-supervised contrastive learning is better transferring to these other tasks than its supervised counterpart. The next thing we wanted to ask was like if we plot on the y-axis ability to match mouse visual cortex, do the contrastive methods that task generalize better, that generalize across more tasks, also match the neurons better overall? So what we see is that a contrastive loss is better match of the neurons than a supervisor or a loss in the same environment. And so again, these are the models that control the body less well, but they're also, as a result, less good models of the neurons themselves as well. And we see this whether or not regardless of what environment we train in, ImageNet or this maze environment, the contrastive is a better, not only transfers better, but also is a better relatively speaking model of the neurons as well. So just kind of the high level takeaway is that this tight relationship between being a better, more task general representation via this contrastive learning and also being a better model of the neurons in mouse visual cortex. And the interpretation is so far is that mouse visual cortex is a low acuity, shallow network that makes best use of its limited resources, of a shallower cortex and lower acuity to create a general purpose visual system that can be deployed in both novel environments and embodied contexts. So now what I'm going to do is I'm going to go to a different species. I'm going to go to primates and humans, and I'm going to go beyond just visual recognition, but to kind of higher cognitive function of planning and mental simulation at short time scales. So this was a work that appeared as a NeurIP Spotlight and done in collaboration with a few folks at MIT. And in particular, the neural data I'll speak to collected in monkeys was collected by Rishi Rajalingam. So the motivation is as follows, is that you and I can like rapidly not only recognize scenes, but we can also draw inferences that go beyond what's in these pixels here, semantic inferences about these scenes. So not only can we recognize that these are ice blocks, but through our knowledge of temperature and dynamics, can infer that the one on the right has been out longer than the one on the left. My cat can also do this. So before she gets on the box, she can predict that this box will support her. And furthermore, just by looking at this image of hats on a rack, I can actually plan intervening actions about how I would take them off. And of course, this isn't restricted to static scenes. We do this readily in dynamic environments as well. So for example, if I show you this video of a fluid hitting an unknown object, you can kind of readily infer that that object was the staircase, just as though it had been there. You can simulate it. So for us, the kind of puzzle was, well, what are the functional constraints that enable the brain's kind of future simulation-like computations across diverse environments? And what we mean by functional constraints is a series of kind of like restrictions on the hypotheses. In particular, that one, they take in unstructured visual inputs like animals do across a range of phenomenon. Given those inputs, they can generate physical predictions about what's going to happen in the future at short timescales. And then finally, from going from inputs to outputs, they consist of internal units that can be regressed against real biological units. So they don't only produce behavior, but they're a neural network that we can actually compare to real brains as they do the same exact kind of behavior. And we call these, just to give them a name, sensory cognitive networks. And our hypotheses, our sensory cognitive hypotheses, fall under kind of like three broad classes, which I'll explain in a minute. But just to sketch the overall idea, is we have pre-trained models of varying of different hypotheses that go from videos, realistic videos, to future predictions. And what we do is, because these are all stimulus computable models, we can compare them on held out scenes for human behavior, as well as completely different scenes that they were never trained on in OOD, when comparing their internals to real brain recordings from primates playing this task of mental pong, which I'll explain now. I'm going to now go into detail about each of these three classes of models while explaining the neural data. So the task that Rishi trained the monkeys on was like Pong, like the game Pong from the 70s, where the monkey is basically operating a joystick to move this paddle. But crucially, as it's about to intersect with the paddle, it gets occluded. And what they found was that across 79 initial conditions of the ball's position and velocity, that in two monkeys, in this kind of part of their physics engine, basically, it was called dorsal medial frontal cortex, or DMFC, is actually simulating the ball's position and velocity while it's hidden from view visually. So the animal's doing this mental simulation in its brain, and they can find that it's doing that computation as it's doing its task. And crucially, what's really cool about the work that Rishi did is that it's recorded from almost 2,000 neurons in two monkeys while it's doing mental simulation. So it's quite a rich data set from a amount of neural data point of view, and it kind of crisply gets at this task of mental simulation. So what I'm going to plot on this y-axis, I'm going to build up a bar plot of how well models predict this brain data while the ball is hidden from view, so during the mental simulation epoch. And so y-axis is the ability to predict neurons, so to regress the artificial units against them, the brain. But first, I'm going to define a NeuroAI Turing test here, and I'm going to show you that because we have two monkeys, we can actually compute the animal-to-animal consistency. And we can see that actually in this task, the animals are quite nicely mapped onto each other. So they're quite highly predictive of each other during this mental simulation computation. So that's good. We can also come up with a kind of perfect simulation oracle, which is the consideration that animals don't only do mental simulation, or at least this part of their brain doesn't do mental simulation, only it can also be responsible for guarding energy resources, also guiding attention, saccades, things like this. And so we're interested in kind of like the portion of the variance that's relevant for mental simulation. So what we'll do is we regress the time series of the ball's position and velocity while it's hidden from view against the neural activity of the brain, and we get that a large portion of this neural predictivity is actually due to simulating this ball. And so that for now is going to be our oracle that we're going to try to meet with the models. So what are the models? So the functional constraint hypotheses. So the first one is end-to-end future prediction. So all this is like the standard kind of generative model that everyone's very familiar with of generating photorealistic future scenes, where you take in visual inputs, you put it through a dynamics predictor, and then you decode the next frame. Of course, the nice thing about this is that it's completely self-supervised, right? You're just doing next frame prediction with a KL penalty to prevent overfitting. And the main thing I want to emphasize here, though, is that its future predictions are very detailed. It predicts the future at the pixel resolution of the sensory input. And maybe this should highlight that this isn't the way you and I do it, right? So while the predictions are very photorealistic, the kind of like planning aspect of it may not coincide with how humans and animals do it. In fact, we can quantify this by comparing the internals of these trained models on videos, this state of the art at the time, to neural data. And what we see is across a range of these, none of them are actually predicting the data all that well, the brain data all that well. In fact, if we took the best of these models in terms of their photorealism, what we see is that when evaluate, they're not trained on Pong, they're trained on videos, naturalistic videos, but when they're evaluated on Pong, like so, their predictions kind of freeze, basically, where the ball actually stops at the final input frame in the model's imagination. So in other words, it doesn't treat it as a moving object. And this is still the case even like if you make the ball bigger or change its shape. I tried all of those. It's sort of like basically overfitting to the environment statistics it was trained on because it has a pixel-wise loss. So when it's given some very OOD scene, it's not able to track and fail to the moving objects. So this is quite bad because imagine if this was in your head as a future predictor, and you're trained on eons of data of moving objects, and then you go to a new room and you completely forget physics, right? So this is why it's maybe too detailed of a loss function because you get to not overfit in the machine learning sense. On test set data, on held out data of the same scenes, it does great. But on a completely OOD environment like this, it fails and also fails to predict the neurons. So perhaps what this suggests is that this part of the brain is instead predicting a kind of factorized rather than very detailed version of the scene. So how might it do that? Well, one kind of very natural suggestion, again, keeping with a self-supervised model, because animals don't get real labels, is a kind of object slot model, where basically you predict at the level of object slots in the relation. So you partition every scene into k object slots, and then you predict the future with a graph neural network, and you predict the relations in that way. And you can do this in a completely self-supervised way, where you contrast that with the implicit dynamics of the pixel-wise model on the left, instead, and basically want to ensure that effectively you want to attract the same slots to one another, but repel them from basically the representations in other videos, which are the negative samples. And what we see is that, again, like across a range of like encoder types, small, medium, and large, none of these models are any better really than these pixelized feature predictors. So if this is the case, it's predicting some factorized version of the scene, it doesn't appear to be by allocating fixed object slots. So the next idea was what I call latent feature prediction, which is rather than posit some kind of explicit latent representation, we learn instead a partial implicit representation of the physical world by performing a challenging vision task, so a vision foundation model. And then what we do is, rather than predict the future state of the environment at the level of the pixels or with these object slots, we hold fixed the vision foundation model and then predict the next latent. So we show the next frame at t+1, get the next latent, and then supervise on that. So then the crux question becomes, well, then what should the vision task be to get this latent representation? So we could start with the kind of like static image foundation models that I talked about, where you're doing this kind of object categorization on ImageNet, or even self-supervised learning on either ImageNet or much larger web scale data sets that are about 400 times larger than ImageNet. And what we see is across all of these, none of them are predicting the data all that well. And one thing to keep in mind, again, is that these are useful for really static image segmentation and classification tasks. But we do far more than engage in static images. So around the time I started this, when I started my postdoc, Ego 4D from Meta came out, whereby participants wear head-mounted cameras and go about their day performing everyday actions. And one thing you can do is you can train a contrastive objective in time where the positive samples are frames that are close to each other in time, and you push away from frames that are in that are later, much earlier in time, and also from different batches in the same slot. And what people have found was that these kind of self-supervised representations are at least better at transferring. They're not perfect, but they're just better at transferring to out of distribution embodied tasks than the prior image static kind of image foundation models latents. And what we see again is that it's only this class of models that are pre-trained on Ego 4D that are starting to like get much further along, closer to this perfect simulation oracle. They transfer better to embodied tasks than the image ones. One thing to keep in mind is that these are all you can ask, like, how much do you really need the additional dynamics training on top of the pre-trained Ego 4D representation? And turns out, as a control, if you did that, if you just compared the encoder and didn't do dynamics, that it's not a good predictor of the neural activity. So you actually do need explicit future prediction in this latent space in addition to pre-training on Ego 4D. So you can't just pre-train on Ego 4D isn't enough. You need to do explicit future prediction. Furthermore, if you did like rather than SSL, if you did this kind of like offline RL on Ego 4D, and tried to push together frames that are closer to the goal state away from those that are further away, this is a less good model. So again, what we're finding is that like self-supervised learning on Ego 4D is a much better model than say like a neural model than offline RL. So, and having this kind of like activity of 2,000 neurons in time helps to really like separate models really strongly. Now, what we're interested in is not just Pong or one environment, but across a range of environments to kind of predict this future simulation like activity. And so we also looked at like held out 3D scenes and so more complex scenes, but with human behavior rather than neural activity. And so this comes from like 8 different scenarios of everyday objects, about 2,000 examples each. And they involve scenarios involving a red agent object acting on a patient object. And the task of the 100 human subjects, which is collected by this group down below at Stanford, is to just output yes or no before the scene, once the scene ends, before it actually happens, whether this contact will happen. So it's like a higher order readout of what you think is going to happen in the future. So to give you an example, here you see the domino, the red domino hit the yellow mat, and here's a side view of that. And then the human subject has to hit yes or no before it actually happens. So they have to like predict this well. And so what we asked is like, is there any single model that can not only match the human behavior, this yes or no thing, which is, on a more complex scene, but like a less detailed readout, as well as match mental simulation in detailed neural activity on a much simpler stimulus where you can train an animal on it, like a monkey in Pong. And the idea is that the reason for this is that like, there's a kind of shared substrate between humans and primates where, humans can play Pong, and primates can also interact in the 3D world really well. So there's some kind of shared computation, and by leveraging both the trade-offs of each data set of human behavior, complex scenes, but simpler readout, less complex scene in monkeys, but a lot more detailed neural activity, we can better triangulate the models and separate them even further. So what I'm doing is plotting, again, same as before. The y-axis is neural predictivity of DMFC on Pong compared to the primate. X-axis is matching human error patterns on this yes/no task. And what we see is that none of the models, again, are like perfect, of course, but what we see is that there's one model that's kind of like closer to this diagonal line, which is exposed to the widest variety of egocentric video sources and transfers the best across the range of embodied tasks. So it does latent feature prediction, pre-trained on Ego 4D and other tasks, and it's the VC1 model. But we still have a ways to go to reach the NeuroAI Turing test, and I'm happy to talk about ideas for better models, which we have some in the works at the moment. But for now, the takeaway here is that mental simulation crucially relies on explicit future prediction of some factorized description of visual scenes, where this factorized description appears to be strongly constrained. Like most models fail to match the data, but crucially must at least enable a wide range of dynamic embodied abilities. So now what I'm gonna do is kind of take maybe a higher level point of view from both of these studies and end more informally on kind of heuristics or lessons for kind of better understanding the constraints of natural intelligence. Um, so, the way in which we kind of get an understanding of the brain, at least from this kind of like NeuroAI point of view, is by incorporating both neuroscience insights, but also AI insights. So in this case, foundation models, high degree of freedom, embodied control, that sort of thing. But from the neuroscience point of view, it's like trying to incorporate two things we can get from the brain: how the brain is connected to itself, that's connectomics, and the other is behavior or ethology. And one thing we see is that there isn't always a one-to-one mapping from a connectome to a functional model, and it's easy to get wrong. And we actually saw this lesson in mouse visual cortex, which I didn't show, but basically, in a nutshell, people had built like, connectome constrained mouse visual cortex models, but they ended up being too deep. And so while they're very detailed, it's much harder to get it wrong, much easier to get it wrong by assuming too much, basically. So rather, what matters more is that the best model can often requires a kind of iterative balance of both functional optimization, so you let the task training fill in the right kind of neurally predictive features with a macro scale constraint, not very detailed connectomic stuff, which can get things wrong, but just things like at a high level, like shallow versus deep cortex. That seems to really matter a lot more for matching mouse visual cortex than anything else. The other is ethology. So looking at behavior doesn't always give us the correct functional target, especially for like intermediate brain areas, like like a visual cortex. So for example, like end-to-end training with RL gives you a poorer match to the neurons for visual cortex than self-supervised learning. So in other words, there appears to be a kind of like, as I'll say this, uh, kind of modularization where like basically what we see overall is like SSL seems to be a good target for intermediate sensory areas. And then RL isn't good for end-to-end learning of those representations to match the brain. But you can imagine that RL is useful towards the end as you go convert those representations into actions. So if I highlight kind of like the takeaways here, perhaps what this suggests is that as we go forward, like engaging with whole brain data, maybe we need more modularized embodied agents. So rather than single brain area comparisons with a single neural network, is to build pre-trained modules, say via SSL, and update rules to try to break down the sensory motor loop, given that end-to-end in a non-RL in a non-modularized manner isn't giving us brain-like representations. So one idea could be something like this, where you build in these modules and they each have potentially either the same or differing objectives. So for example, SSL in the perceptual module. And it can, try to address this question of how does the brain represent, predict, plan, and enable action? So to be able to reverse engineer the full kind of sensory motor loop that an animal undergoes. So I think to get at these kind of embodied agents, or what I call a neuro agent, there are some core AI challenges that we still need to solve in each of these modules to better connect them to one another, which I've just kind of highlighted here, and I'm happy to discuss further at some point. But the main idea is that basically, and here I'm just using the rodent brain as one example, is that once we get there, each of the modules is functional hypotheses for individual brain areas, and the agent as a whole, so these black arrows, are a hypothesis for how they connect and interact. So for example, connectomics can inform connections between large-scale brain areas as opposed to within module, which is how it's currently applied. And now what could we do with this type of neural agent that we couldn't do before is one, not only would these be open source benchmarks, neural data is becoming more and more open source as neurotechnology is enabling us to record from whole brains more easily while in animals performing behavior. But we can also basically, have leverage the community and like publish these models, of course, in an open source way. But the community can then use them to predict outcomes from new experiments, right? Doing biology is hard, takes a long time. But if you could run millions of interventions in a model, then that can generate predictions for new experiments much more quickly if you had a neurally faithful model of the brain. But beyond like kind of simulating things and predicting outcomes, it also provides us with a systems level understanding of an organism. So one thing is that uh, in open-ended environments, there isn't a well-defined reward function like there is in games like Go and chess, where RL has been very successful. And so understanding what these hardwired, these intrinsic goals that make animals autonomous and build towards autonomous agents is going to be kind of quite critical. And we can use these kind of agents as a platform to explore that. So imagine you have these modules and then you're training it with a high level intrinsic goal, which is your hypothesis for how the animal is actually exploring its environment. We can also specify update rules for these modules. So this can be helpful for identifying biological learning rules, where you stop the pre-training and then you start the online experience and then compare it to real neural data of while an animal's learning. But even from an AI point of view, this is important because, test time reasoning is kind of like the simplest version of this, where you do adaptation online. We want our agents to be able to adapt to new scenarios, which, our current models don't do a good job of. But test time reasoning doesn't update the weights. And so it's just the beginning of this kind of like online learning that we want to get without catastrophic forgetting. So we want to somehow do some kind of weight updates in each module without catastrophic forgetting. And how to do that, I think, is still an open question. Finally, the other thing this allows us to engage with is to understand kind of species conserved algorithms across modules. What I mean by that is that this sensory motor loop is conserved across species. Mouse, primate, human, they all do it. So not only are we not restricted to any one animal, we can imagine having embodied agents for each different animal species that we study. So here I'm showing in the circle like the brains of rodents, macaques, and humans, and I'm highlighting the homologous brain areas that are all involved in the sensory motor loop that are color-coded by each potential module. Now, in the foreseeable future, what I think of this is that basically this allows us to study, what algorithms are conserved across species and which ones differ. So, for example, in the perceptual module, both this contrastive SSL loss not only predicts mouse visual cortex well, but also primate visual cortex well. But the main difference is that primate visual cortex is much deeper and hierarchical. Mouse visual cortex is much shallower and less hierarchical. And what you find is that despite them being unified by the same self-supervised loss that best predicts neurons, the difference in their constraints and their architecture yields, in the case of primates, a better feature representation for object recognition. It's better at recognizing objects, whereas in the mouse, it just tries to be as general purpose as possible, but still not, in absolute terms as great as the primate, but just as good as possible across a range of tasks. So this is what I mean. It's like the species conserved nature of this is that the two kind of species right now, as far as we know, are unified by the same SSL objective, but satisfy different architectural constraints of shallow versus deep, which give rise to different abilities of doing well in object recognition, like in primates and humans, and be able to manipulate objects when you're deeper, and less good in rodents. So kind of my last slide is, what happens once we get there. This is a neuroscience base, but just more broadly speaking, as we build more capable agents. Right now, there's a lot more effort in AI on AI capabilities than in safety. So safety is a recent direction I've become interested in. So I'll just have one slide for this, which is that one can prove theorems about agents that are unbounded in capability, and the idea here is that we can show in theory that things are hard even for unbounded agents. And so if something's hard for unbounded agents, then we should avoid this in current practice. In particular, what this theorem is showing is that basically if you have too many agents and too many tasks that are trying to agree on something together, so imagine like you and your robot are trying to agree on a task of, like, say, making a sandwich or doing a nuclear power plant and things like that. If you have too many tasks and too many agents to align over, then what this shows is that it's impossible to align them efficiently. The number of bits they need to exchange at minimum to guarantee this kind of alignment, this inexact alignment, approximate alignment with high probability, ends up scaling linearly with the number of agents and the number of tasks. So what this suggests is that actually, even if you're computationally unbounded, this could be an issue. So in other words, you should choose your tasks and agents wisely. Another aspect of this is that, like, a lot of people are suggesting that brain-computer interfaces are maybe a way forward towards ensuring that we align with like super intelligent AI. But what this theorem shows is that actually brain-computer interfaces won't solve the alignment problem because in cases where you have too many tasks and too many agents, the minimum number of bits exchanged would be too large. So not only does this idea fail just more simply because our brains are constrained, but even if we were unconstrained, this would be an issue because the number of bits exchanged would be too large if you have too much of M or N. So instead, what it suggests is that the AI safety community should focus on a small number of agent subgoals or utility functions, so a small number of objectives M that lead to better incentives for us. So how to do this is an open question, but it kind of ties back into this neuroagents thing I was showing you where we want to better understand the intrinsic goals of animals, but in particular, if we're going to build AI that also does useful tasks for us, we should ensure that those goals, those intrinsic goals, which aren't well defined in open-ended environments, but have to be specified by us, are aligned with our human incentives and values. So in any case, I'll end with that and thank my wonderful collaborators and funding resources, both across institutions at CMU, Stanford, MIT. Thank you so much.
Thank you. Thank you. Thank you, Aaron. Anyone have any questions?
Oh yeah, hi Aaron. Great talk. Yeah. Yeah, I have a question about especially your neural agents idea is pretty interesting. So I want to ask in the future, if you finally get there, what kind of evaluation metrics do you want to create?
That's a great question. Thank you.
Yeah.
Yeah, so this kind of goes back to the beginning of the talk where we had the NeuroAI Turing test. So I kind of think of this as like one of the things I'm interested in is to try to see, are these agents like matching brains as well as brains match each other? So on a variety of benchmarks, as many as possible, can they
Mhm.
kind of reach the respect? Each benchmark creates its own NeuroAI Turing test. Are these agents matching that across them? And the nice thing about these agents is that because they're stimulus computable, in other words, they also take in unstructured visual inputs, you can
Mhm.
deploy them in a variety of new environments. And so not only does this give you flexibility to test them across benchmarks, but it also allows you to generate new predictions too.
Mhm.
Because the thing is right, it's like the thing then you're only constrained by at that point is like what scenarios you can actually like test animals in and get recordings for to like be able to like evaluate the model. And so in a lot of cases, I imagine that it's actually much easier to generate a prediction and then wait, however long it takes for the technology to catch up to be able to like record from the animal. And so I feel like in a lot of cases, it's going to be like it'll be faster to generate prediction in the model, and then you can
Mhm.
go back and compare it to the animal up to the NeuroAI Turing test is defined for that benchmark, up to how, for multiple animals you'd have to record and compare how their recordings to each other match before you then evaluate the model to the brain.
Yeah. And yeah, currently for vision model, we have brain score, or for a neural representation, we have some RSA stuff. Do you think these metrics can still be applied to neural agents?
Definitely, I think so. And in large part, what you see is
Uh,
despite those metrics being different in formulation, they yield pretty similar at large scale conclusions. So I could imagine applying any of those to the individual modules that I was showing you in the NeuroAgent. So each of
Mhm.
these basically compared to each brain area. And what you want to see is what the respective kind of NeuroAI Turing test is for each brain area here that's highlighted, and then checking if the module matches that brain area well. Um, and yeah, and I think I tend to prefer predictivity, like linear predictivity, because one reason is that it's also useful from an engineering point of view. So in other words, imagine if you build a linear map that predicts the neurons to say this brain area, then you can actually backprop through it and generate a stimulus too. And then use that for BCI, for brain computer interface, to like control the neural population as well. So if you can predict it linearly, then you can also control it quite well. And that's kind of useful as its own. If you wanted to do BCIs, maybe that's helpful. Yeah. So beyond like scientific conclusions.
Cool. Yeah, and another follow-up. Yeah, I think this figure is pretty good. Yeah, basically you think the neural agents like can be integrated using different modules. Is it going to be a end-to-end models, or you want to train neural agents separately?
I could imagine pre-training the modules initially
Uh-huh.
separately, or kind of in a higher sequential way, in a
Uh-huh.
hierarchical way as they build on top of each other. But ultimately, you would then do online adaptation end to end, like test time adaptation, basically. Yeah, that would be done.
Oh,
Yeah.
yeah.
I mean, the modules here are really just like approximations. So like in principle, right, you could by the universal approximation theorem, like train something end to end that like mimics this, like without modularization. It's just that like you often have finite amount of data and resources, so it's far more efficient to have these kinds of inductive biases to than to collect a way more multimodal data, interaction data than you could ever get to be able to get this to work well. Yeah. And we see this kind of modularization where, so far right now, our best theory of the perceptual module is kind of contrastive SSL objective here. And then like RL is more towards the motor module rather than end-to-end RL. Because like when
Mhm.
we end-to-end RL, the perceptual module, we see less good neural predictivity in both rodents and primates. Yeah. So even from a brain point of view, it does seem that there's modularization to some extent.
Cool. Yeah.
Well, thank you.
That's all my questions.
Thank you, Pingyuan, for all the wonderful questions. Anyone have any other questions? Okay, I have a few. Uh, so for like the self-supervised learning actually did quite well to predict the visual cortex. Like self-supervised contrastive loss is actually quite good, like aligned in the visual cortex. But the reinforcement learning doesn't. I was wondering, like, like when do you think about embodied data? If you like, what does that mean to have like self-supervised embodiment, like self-supervised learning of embodiment? Something like that data set should be, you should have all the vision, you should have all the actions, you should have all the like proprioception, touch, like everything. Like imagine that some of that data set exists. Do you think like self-supervised learning on that embodied data set is going to create something that's more like the brain than some kind of reinforcement learning like based like trained end-to-end neural
No,
network?
so I think you'll need RL. So RL is the most general formulation of this. In fact, like you can like show that there's a like SSL is like a subclass of RL anyway, like without actions. So in other words, it's like a special case. So like I imagine eventually you need RL anyway. So I don't think that like the SSL would supersede things. It's just that SSL is useful to do up front because it allows you to learn a general purpose representation that then can be adapted by RL to convert to actions that are relevant for a particular context. That's kind of how I like to think about it.
Yes, but like I think what I'm trying to say, like what if like the action itself is also a representation? Like um I think what I'm trying to say is that you can imagine that you can collect a huge motion database, right? Like just like people performing all kind of actions. Like then the action itself also become a data set, or uh like like something that you can do like self-supervised learning on or unsupervised learning on.
Oh, so that's what I showed with the Ego 4D. So that mod, like the offline RL thing that I was showing, that's basically that idea, but applied to Ego 4D. And at least in on this data, it led to a less good model of neural responses in mental
Oh
simulation.
yeah, like yeah, that's true. Like Ego 4D essentially. Yeah, that's correct. Yeah, okay. Yeah, oh that okay, that's interesting. Um And the second question, like, what does consciousness plays a role in this map? Do you think like something like AI to get to consciousness, like need some kind of like embodiment? Like, do you think that's going to be the like phase transition, or it's just another story, like just like increasing the modality of the data, something like that?
I think so. I think with consciousness, it's hard to say because we don't have like a definitive test in the brain to really test it. So it's hard to like know what it'll be useful for or not. But I think like whatever that is, like in terms of my own informal definition or working definition of consciousness, is like I do think that like probably you don't need embodiment for it. And like if it's digital, it's like in some sense embodied in that there's a kind of boundary between the agent and the environment, where in this case the environment isn't the real world, but it's the web or it's digital, right? And so um, that agent will be not physically embodied, but digitally embodied. So at that point, I think that the more essential thing will be the cognitive architecture. But you need a test, like one would need to, like, the main problem with consciousness science, and the reason why it's very difficult to like falsify anything is that you need to have a definitive test of like what should be in the architecture and the representations in a brain for us to be like, okay, maximally the brain is conscious, and therefore we can like apply that quantitative metric to models. Like all my work, right, that you see here is quantitative and metric based. We need something like that for something like consciousness, and we don't have anything close to it or even a consensus. So that would be like obviously the first step. But I do think it'll come down to like some criteria about the architecture of this kind of agent, what the arrows are, but also like what's the representations in these modules to be able to determine that. But I don't think embodiment is the key. I mean, it's trivially embodied even digitally, right? Yeah, I think that's fine. It'll just come down to those details of the agent architecture and representation.
Yep. Thank you. Um, does anyone have any other question? If not, I will ask like another question before we close. So, Aaron, like, what will be your next step? Like, what like your most exciting next like architecture that if like you are going to build, like following the roadmap, like here, like what exactly are you going to build? Are you going to build some vision language action models? Are you going to build some transformer models or like visual pre-training following RTM? Or like there's also visual language pre-training, like which Percy Liang and people have done, which they bring the language like architecture stuff into this kind of models. And then like I wonder, because you show the RTM, I'm wondering like then there's the Voltron, right? Like which is the visual language like pre-training representations. Like so what's the next step? Like exactly your like the which architecture like you are going to build to align with the brain data. Yeah.
I think it's like less like architecture at the moment for us and more like actually figuring out this question of the intrinsic goals. Because I think that's a very deep question of like how do you get a true autonomy in an agent, and like especially in environments where there isn't an external goal. So right now it's kind of like even taking existing architectures and trying to get agents that have reproducible and reliable behavior, better than kind of just like standard RL techniques, is a goal for us in the short term. Um, in the long term, I think things like, memory matter, like what architecture is there for like long context and long horizon reasoning is another challenge. So all of these things are gonna matter. Like, online autonomy basically is what these intrinsic goals get at. And like the memory as well as like role modeling and embodiment are all going to be kind of the major challenges that are important. But for now, we're starting with these intrinsic goals because I think that matters a lot more to us, where we want to build kind of creatures that do like work in open-ended settings, and maybe less as a product outcome, but more for like a just building lifelong learning agents is quite critical here.
That's actually related to the proof you share with us just now, right? Like you cannot have too many goals, like like so like do, what are some goals that you have been thinking about? Like I mean like evolution is like has only one goal is reproduction. Like it seems like the
Yeah.
like,
I mean, I think that'll come down to like, well, it depends on what your endpoint is. So like if your endpoint is a safe, reliable system to be deployed in the real world, then I think you definitely need a few goals. And those need to be aligned with things like honesty and the ability to, be able to verify the accuracy of things, but also not cause harm at the level of its own. Like it should be robust to self-preservation, but also not do so at the expense of the preservation of others, right? As one example. But I mean, for us, like, not like stepping away from like safety, which is, in particular for systems that'll be deployed in the real world as products, more so just like understanding it here is like, survival is very hard if you want to build just a creature, is hard to like instantiate to do useful things. But something about like basically keeping track of like world model updates and progress there from what we're finding, and we should have a paper on this soon. Yeah, it seems to be like more salient at least there. So like kind of orthogonal to the safety stuff, but just simply like getting an agent that like doesn't waste energy on like things that are maybe information theoretically like white noise useful, but like for real animals in the wild, like they wouldn't waste and spend their energy on. So if they can predict with their world model that something's going to cost them energy and they can avoid that and track progress, then I think that's very valuable for a robot, but also just like what we see actually in real animals today too. So we'll have a paper on that soon. But that's sort of orthogonal to the safety thing, which is like if you want a product in the world, then you want a very small set of values because you want it to align with our incentives. And so if you want it to align with your incentives, then you do have to specify a small set of goals. With, for example, things like honesty and self-preservation without being at the cost of the preservation of others.
Yep. Yep, I agree. Yep. Yep. So thanks, Aaron. Like we have a wonderful talk, slightly run out of time. I will end the recording now and like